Hi everyone, welcome back to our Python for Data Science series. In our last session, we wrapped up our introduction to algorithmic complexity, big O notation, and fundamental searching and sorting algorithms. If you haven't seen that yet, make sure to check out session 4 linked in the description below. Today, we're taking a massive leap forward into section 5, where we will focus heavily on how data science workflows handle data structural organization, unexpected system behaviors, and external information. This session covers dictionaries, sets, tuples, error handling, and debugging. One of the superstars in Python data structures is the dictionary. What exactly is a dictionary? Till now, we've been using lists to store collections of data. In a list, your data is ordered and you can access it by its physical position, its integer index, like 0, 1, 2, 3, and so on. But real world data isn't always sequentially numbered. Think about a physical English dictionary. If you want to find the definition of the word algorithm, you don't open the book and start counting. Okay, let me check page 1, now page 2, page 3, and so on. That would take forever. Instead, you look up the word itself to instantly find its meaning. This is exactly how a Python dictionary works. It is an unordered collection of key-value pairs. The key is the label you use to look something up. The value is the actual data attached to that label. Instead of using a number to find data, you use a meaningful key, like a name, a product ID, or a date. In data science and software engineering, you will see dictionaries everywhere. Here are three classic places where they are indispensable: user profiles and address books, JSON and web APIs, database records and configurations. You might ask, why can't I just use a list of lists to do this? There are two massive problems with that approach. First, it's highly counterintuitive. Take this example. Here, to find Ellie's email in the list, your code has to run a loop. It looks at index 0, checks if it is Ellie, then index 1, then index 2, and so on until it finds her. It's clunky to write and slow to read. Second, it completely destroys your performance. Searching through a list is a linear time operation, or ON, in big O notation. If your list has 4 names, it's instant. If your data science pipeline has 10 million rows, a list lookup will grind your computer to a halt. A dictionary, however, uses an ingenious computer science mechanism called as hash table. Without going too deep into the math right now, a hash table takes your key, runs it through an algorithm, and computes the exact memory address of the value. Because of this, looking up a key in a dictionary takes constant time, or O1. It doesn't matter if your dictionary has 4 elements or 40 million elements. The lookup is practically instantaneous. There are two golden rules for dictionaries. Keys must be completely unique. You cannot have two identical keys. If you try to add a second entry for Ellie, Python will simply override the first one. Keys must be immutable. You can use strings, integers, or tuples as keys because their values can't change. You cannot use a list as a key. If a key could mutate, Python would lose track of its hash location and the structure would break. Values, on the other hand, can be anything you want: lists, numbers, strings, or even other dictionaries. Now that you exactly know what a dictionary is, why it's light years ahead of a list for lookups, and how it keeps our data science pipelines incredibly fast, let's run the code. We will initialize our very first dictionary named email dict. Notice the syntax. We use curly braces, colons to separate keys from values, and comma to separate the pairs. When we verify the type, Python confirms this is a built-in dict object. To access the data, we pass the key Ellie inside square brackets and boom, constant time lookup. But look what happens if I try to call a key that doesn't exist, like Fred. Python immediately throws a key error. This is the perfect example of an exception which we will learn to catch safely later in the session. Let us see how we can dynamically build, update, and prune a dictionary during runtime. We can instantiate a totally empty dictionary using the dict function. Adding items looks just like list index assignment, except we are assigning data to string labels instead of numbers. If Ellie updates her email address, we can use the exact same assignment syntax to update the value. Because keys are unique, Python silently overrides the old email with the new one. If Fred leaves our team, we use the dill keyword to wipe out his key value pair entirely. We can then use the in keyword to verify membership, which returns a boolean true or false. When writing data processing scripts, you'll constantly need to iterate through these collections. Let's look at how loops interact with dictionaries. Take a close look at the output. When you run a plain vanilla for loop over a dictionary, Python loops through the keys by default, not the values. Also notice, because dictionaries are unordered, items might print out in different sequence than how they were inputted. If we want both components, we can either look up the key manually inside the loop or use a much cleaner .items method which unpacks both variables at once. If you only care about the data payloads, use .values to skip the keys entirely. Now that we have mastered dictionaries, we need to talk about the remaining two core data structures built directly into Python, sets and tuples. Just like lists and dictionaries, these are collections used to group data together, but Python didn't create them just for fun. They exist because they solve specific structural, mathematical, and performance issues that lists simply cannot handle efficiently. Let's look at exactly what they are, where they are used, and whether they matter to a data scientist. What is a set? Think of a set as a highly strict version of a list. Formally, a set is an unordered collection of completely unique items. Imagine you're analyzing a log file of web traffic for an e-commerce store. You have a list of millions of IP addresses that visited your site today, but many users clicked around and refreshed pages, meaning their IP addresses appears dozens of times. If your boss asks you how many individual unique customers visited our site today, a list won't help you directly. You would feed that messy list into a Python set. The moment you do, Python instantly strips away every single duplicate, leaving you with a collection of pure, unique values. Real world use cases of sets, removing duplicates, permission and access control, mathematical relationships. Just like dictionaries, sets use hashing under the hood. If you want to check if a specific username exists in a list of 10 million users, Python has to loop through the list, which takes linear time, O(n). But checking membership in a set takes constant time, or O(1). This is lightning fast because Python mathematically calculates exactly where that item should be rather than searching line by line. Now, let's run some code. If you have a list with duplicate items, passing it to the set function will create a set that only contains the unique elements. Alternately, we can create a set by replacing square brackets with curly braces. Standard operations on a set like adding, removing, union, and intersection are methods that are present within a set. Looping through a set works much like looping through a list. With the in keyword, we can check membership inside a list at constant time. Now, let's talk about a tuple. A tuple is an ordered sequence of elements, meaning it preserves positions just like lists, but with one massive catch. It's completely immutable. Once you create a tuple, it's absolutely frozen. You cannot add items, remove items, or change the value of an element. Think of a list as a dynamic array where things change and a tuple as a permanent record. For example, if you're writing a script that handles geographical data, the coordinate point is a perfect tuple, latitude, longitude. If you change either number, you're no longer talking about the same location on Earth. It should be immutable. Real world use cases of tuples involve data protection, dictionary keys, and multiple function returns. Let's look at some code. We can create tuples using parentheses instead of brackets. We can access, slice, and loop through tuples just like lists. Since tuples are immutable, if we try to change a value, we will get an error. Take this function where we have multiple outputs. Now if we call this function, we get a tuple as an output. If we wish to assign the values to different variables, we can use multiple assignment. Quick summary, to keep it simple, lists are ordered, mutable, and allow duplicates. Dictionaries are unordered with unique keys mapped to values. Sets are unordered, completely unique elements with incredibly fast lookups. Tuples are ordered, completely frozen, and immutable lists. Now that we've covered Python's primary data structures, lists, dictionaries, sets, and tuples, we need to talk about a feature that completely transforms how you interact with them. It's a concept called comprehensions. When you start looking at professional data science code or open source Python packages, you're going to notice that developers rarely write traditional multi-line for loops just to create a new list or dictionary. Instead, they use comprehensions. In the Python community, we have a term for the code that is clean, highly optimized, and follows the absolute best practices of the language. We call it pythonic. Comprehensions are the epitome of writing Pythonic code. They allow you to combine looping, data transformation, and conditional filtering into a single, elegant line of code. Understand why comprehensions are powerful, let's think about how we normally build a list. Say you have a data set of numbers and you want to calculate the square of each number to use in a machine learning feature. Using a traditional loop, you have to write three distinct lines. First, you initialize a completely empty list. Second, you write a for loop through iterate your data. Third, inside the loop, you perform the math and explicitly call the append method to push that new number into the list. It works, but it's verbose. It forces Python to constantly look up and execute the .append method over and over again, which adds unnecessary overhead. A comprehension collapses the entire process into a single line inside square brackets. It reads almost like a mathematical definition or a plain English sentence. Give me the square of every item for every item in this sequence. The basic blueprint looks like this. Mapping of an item for item in sequence if filtering condition. Mapping You can apply a transformation or a function to every single item as it goes through, like squaring a number or converting text to lowercase. You can add an if condition at the very end to act as a gatekeeper. For example, I only if it is an even number. And here is the best part. Comprehensions aren't just for lists. You can write a set comprehension or dictionary comprehensions too. Using curly braces to map keys to values instantly, it makes your data processing pipelines incredibly concise, fast, and easy to read. Up until this point in our data science journey, we've been working in a bit of a perfect world. We write our code, we feed it clean inputs, and it runs exactly as expected. But as your data pipelines, machine learning models, and automation scripts grow in size and complexity, you're going to hit a universal truth in software engineering. Your code will break and errors will happen. In data science, this is amplified times 10. Real world is incredibly messy. You may write a script to scrape web data and the website suddenly goes down. You may expect a column of numbers, but a data provider accidentally sends a column of text. If you don't plan for these anomalies, a single missing file or a single formatting typo will cause your entire program to crash spectacularly right in the middle of production run. Today, we're learning how to build crash-proof code. Take this function as an example. Miles to kilometers returns miles into 1.609. When Python encounters something it cannot execute, it throws a fit and it hands you a giant wall of red text called as a traceback. To a beginner, a traceback looks terrifying, like your computer is screaming at you. But as a seasoned data scientist, you must learn to view the traceback as your best friend. It's a precise diagnostic map. When you look at the traceback, you always want to look at two key parts. The target line. The traceback points a direct arrow to the exact line of code that triggered the failure. The exception type. At the very bottom, states the exact legal category of the error, such as type error. You see exception handling in the software you use every day. Think about filling a form online. If you accidentally type date in the wrong format, the entire website doesn't crash and show you a raw error screen. Instead, the system interceptively catches your mistake, displays a clean message, and politely prompts you to try again. In Python, we achieve this exact resilient behavior using a try except block. The concept is incredibly straightforward. You place your normal, risky code inside a try block, telling Python, hey, attempt to run this code safely. Right below it, you define an except block targeting the specific error type, telling Python, if a type error happens, do not crash the program. Jump down here and execute this fallback plan instead. By handling exceptions explicitly, you can gracefully log data anomalies, substitute default values for missing data, and keep your multi-hour data mining scripts running smoothly from start to finish. We have covered a massive amount of ground today. Thank you so much for watching. Keep coding, keep debugging, and I'll see you in the next session.